Let me get this going here. There we go. Rationalizing radical expressions, with this word rationalizing kind of being the new thing. So I've just written a few statements up here for various reasons, and I'll get into those a little bit today. Formal communication with math requires that a radical not be left or remain in the denominator of a fraction. Let's talk a little bit about what some of those various reasons are. Some of them are historic and some of them are very contemporary. So the old historic reason for why it's not okay to leave like a square root or some of the radical in the denominator is simply because calculators, to be honest with you, are a very recent invention in the grand scheme of math. So for example, when I was your age as a freshman in high school, it was 1989. Calculators had been around for a long time. Graphing calculators, similar to the ones that some of you have, were extremely new, just coming around in the last year or two. For when I was in ninth grade. When I was in 6th or 7th grade, we had very, very rudimentary calculators. Graphing calculators were still really not even that much of a thing that like normal people would have. And if you go back even 10 years from there, then calculators, even the really simplistic ones, were very expensive. Go 10 years prior to that, and almost no one had calculators. Certainly no one had computers, right? And so in this time frame, in the not that recent past, when you didn't have calculators, the way that you would divide things that had radicals, it was much easier to not have a radical in the denominator when you were actually going to be doing division and actually doing some serious computation to get to an answer, right? To get to an approximate answer at least. So it doesn't really apply anymore, right? There's two far more contemporary reasons. One of which has to do with programming, being able to manipulate expressions to get them into a form that's easier for a computer language to be able to manipulate and read. The one reason that's probably the most in the forefront of my mind is next year when you guys take geometry, part of geometry covers trigonometry. Have you guys ever heard of like cosine, sine, tangent, anything like that? If you haven't, next year you certainly will. And with those trigonometric concepts, your ability to move a radical either into or out of the denominator and recognize the equivalent forms that result from that it'll be very important from the perspective of you need to be able to recognize when two things are equivalent and you need to be able to see it immediately. And getting a little experience with this will help a bit with that. Okay? There's a couple of reasons. The one that's most in front of you is you're going to need this to be able to communicate effectively when you get to trigonometry. Something to think about. So I think you're going to find this to be not that difficult. So it's a good thing. Just I'm trying to lay the groundwork for why. Because just to be honest with you, later on if you do take like an upper division class, like maybe a calculus class or whatever, we're going to relax the rules a lot. We're going to be like, it's okay to leave it a radical in the denominator now. And we'll have our reasons for that. I just want you to know kind of why we want you to be good at being able to recognize these different forms of things. Okay, so terminology-wise, if a fraction has a radical in the denominator must be rationalized. That's that word I've used a couple of times. The denominator must be rationalized. And effectively what that's going to do is that's going to move the radical out of the denominator and put it in the numerator. And we'll talk about how to do that. First thing I wanted to ask you guys, and this will just be a quick little exercise for you. If you take a look at letters A, B, C, D, E right there, some of these are going to be really, really easy. Some of these are going to be just a little more tricky than others. My question to you is, for A, B, C, D, E, all 5 of those, which of those would need to be rationalized? For some of them, the answer is going to be yes. The others, some they're going to be no. Some of them are going to be a little tricky. So I want you guys just to think about it for a second. Feel free to discuss if you want. I want you to take your pencil on your paper, and I want you, with A, say, does this need to be rationalized? No or yes. Does this need to be rationalized? Yes or no, whatever. I want you to put like no or yes to go with each of those, all right? So ready to go. And I'll get your answers here in a second. We'll try to get this figured out. Which of these has a radical in the denominator, and we're going to have to go through this rationalizing process? Yes, sir.
Just to see if so it says if the radical cannot be left in the denominator, and that's basically what makes it rationalized.
Well, yeah, it means you need to rationalize it.
Yeah, so does that mean just if there is a radical in the bottom, then that's automatic?
I would say in general, yes, but some of them are going to be a little trickier than others. But I mean, what you're identifying is absolutely the first thing I would look for.
Okay.
But then, well, with at least one or two of these, we're going to look a little deeper.
Okay.
And we might change our minds. Maybe it doesn't.
Okay. Thank you.
You bet. Okay, so for letter A, it's all binary. It's either yes or no. For letter A, do you think A needs to be rationalized?
Yes.
All right, so we say yes there. Anybody want to volunteer a reason? Like, what was your kind of initial idea of, like, yes, this does, and why? Why do you think that this needs to be rationalized? There you go. There's a radical in the denominator. I see it right there. Square root of 5. That's a problem. We're not supposed to leave a radical down there. We're not supposed to leave, I've heard it termed, you're not supposed to leave a rat down in the basement. You got to get it out of there, whatever. So I agree with you. A needs to be rationalized. What about B? Yes or no?
No.
You guys are correct. You obviously saw that there's no radical in the denominator for B. So the answer is no, it does not. How about C?
Yes.
I didn't think so.
Yes or no? You say no. This is the first one I've had some disagreement. I heard some yeses and nos. You say yes.
I have no idea.
Ava, you say no. Why?
I don't know. I could be wrong, but since there's one on the top and the bottom, I thought it was the same as just having one big one over the entire thing. I don't think that needed to be fixed.
So the truth is, okay, so there's definitely a lot of truth to what you're saying. So the square root of 5 over the square root of 4 could be rewritten as the square root of 5/4. We've talked about that a little bit the last couple of days. You're 100% correct. But even still, when you have like a big radical over, with a fraction in it, you still technically have a radical in the denominator, don't you? So I don't think we can like just change the form. Be like, hey, no, it doesn't have one. It still kind of does, right?
Okay.
So have you changed your mind? You say yes now? Or are you still saying no? It's okay. I just... Okay. So does everyone in the room say yes?
Yes.
Interesting. The answer is actually no.
Okay.
What is this nonsense?
What's the square root of 4?
2.
So this is really square root of 5 over 2. Does it have a radical in the denominator, really? Does this need to be rationalized? No, it does not.
Oh, but 6.
I told you one of them would be tricky. I told you one of them would be a little tricky. Make sense?
Yes.
Okay.
I did not get them all right.
So maybe, do you want to reconsider D and E now?
No, because
No?
they don't have that.
Okay, so D, what do you guys say, yes or no?
Yes. You said one of them. No.
D?
Yes. It's yes. It's yes.
For D, raise your hand if you think the answer is yes. Raise your hand if you think the answer is no. So everybody says yes. No, Kyrie is... Are you just trying to be...
No, I'm going to actually see if I'm ready.
Okay. So let's check this in a similar way we did with C. Obviously, C and D look similar. The square root of 4 was 2 in C, right? What's the square root of 6?
Oh, I know.
It's not quite so nice, right?
It's not a whole.
It's not a perfect square leading to a whole number, right? And so I think this one we'd have to say yes, it does need to be rationalized. What about E? Square root of 8? Could we break that down like we did the square root of 4?
Yes.
What's the square root of 8? Yeah, it is 2, but again, it's not an integer, right? It's not a perfect square. So I think the answer here is yes, this does need to be rationalized. Okay. What do you guys think as far as identifying when you need to rationalize? You okay with that? Okay. Okay. So I would like now to show you, or have maybe you figure this out. How do we actually do this? How do we rationalize the denominator?
Essentially just move it from the top to the bottom, right?
You can't just we're going to have to do something like that. So guys, I want to give you this example here. 7 over the square root of 2. Based on the work we just did, you guys see how this one, we do really have a radical in the denominator? You see it right there, square root of 2.
Yeah.
So based on the factors I told you earlier, we can't leave it like this. It's not all the way simplified.
Yep.
So Any ideas on what we'd need to multiply by here? I mean, Ava was starting to think maybe I need to do this or that. What do you think?
Multiply by the square root of 2.
So multiply what by the square root of 2?
Both.
Both what?
The numerator and the denominator.
Okay, so let's think this through. So I multiply the denominator by square root of 2 and the numerator by the square root of 2. Let's think about how this would work. What would you guys think the square root of 2 times the square root of 2 would be?
Nothing.
It's not nothing.
It would be 2.
It's the square root of
4.
4, which is 2. Look at that.
Goes back to what it was.
Oh, wow.
So it's the square root of 4 down there, and the square root of 4 is 2. Interesting, right? We haven't dealt with the numerator yet, but there's the denominator. Does that make sense?
Yes.
And do you see how, at this stage, there is no more radical in the denominator?
But you still have to multiply the top.
We got to deal with the top. You're right, we do. But I just want to make sure you understood that part. Denominator, okay? Now, in the top, we're gonna go in depth with this more next week. In the top, did you guys notice that, of course, the root 2 is a radical, right? It's a square root.
Yeah.
Did you notice that the 7 is not?
Yeah.
So whenever you have this situation, you simply are going to multiply the 2 together just by writing 7 times the square root of 2. 7 times the square root of 2. It is not 14 or square root of 14. You could prove that to yourself with your calculator, perhaps. But anytime you're multiplying a radical times a non-radical, you just multiply them together and just group them like that. You can't directly simplify
Would that be
them.
the final answer? Though?
That would. 7 root 2 over 2. It would be.
Can it happen like that if it's a prime number?
Can it only happen like that if it's a prime
If
number?
it was like an 8 instead of a 7, would that still work?
Oh, yeah. You're talking about this number right here?
Yeah.
Yeah, totally. Now, if the 7 was an 8, then, of course, 8 over 2, like if this was an 8 right here, 8 over 2 is 4, right? So you could simplify that a little bit further if it were like that. Yeah. Okay, so I really think that number 1 is super similar to what we just did. So I want you guys to try number 1, okay? We'll do some more complicated ones here in a second. But please try number 1.
9 root 5.
2 is a little more complicated than the number 1. So please practice this one with me, and then I'll leave you guys up to do number 3. So this one, do you guys recognize the radical in the denominator?
Yeah.
So you might say, all right, let's multiply by root 12 on the numerator and the denominator.
Oh, but that can be reversed.
Perfectly reasonable to do. Maybe you do it this way. So if you do this, you get 3 square root of 12. You're confused?
No, he feels abused. I
Oh.
feel abused because Kyrie told me to shut up.
I think it's perfectly reasonable if you're talking while I'm talking and she tells you to be quiet. I think it's perfectly reasonable. Yeah. So then square root of 12 times the square root of 12 is the square root of 144. Right? And what's the square root of 144? 12. So hopefully you're starting to see this pattern about how this radical can kind of move up and down a little bit. There's a little more to this one than just that, right? So let's talk about some reducing. There's multiple reducings here. Did you guys notice the 3 and the 12? Isn't that a reducible fraction? What is 3/12 reduced to? So look at that. So 1 and 4. So this would be 1 times the square root of 12. Or really, honestly, isn't that just the square root of 12? All over 4. The truth of the matter is, there's a little bit more we could do, because this said, practice rationalizing and simplifying. It's not all the way there yet, is it? Anybody see it? The square root could be simplified.
Simplified 2 3.
So check, yeah, that's right. We can break it down prime factors. So square root of 12 is really square root of 2 times 2 times 3. And just like you guys did a nice job on the board on certainly more complicated expressions, aren't there... Oh, I'm sorry, did I go too fast?
Way too fast.
No, I just
I got lost.
Where did you get lost?
That's a good question.
Coy, go ahead.
What did you simplify?
Shh.
Why did you break it down into 2 times 3 times 3?
So I recognize that 12 was not prime. And if you remember from what we did yesterday, anytime you've got the square root of some number, you want to consider, is it all the way simplified? Oh, and I just did a mental factor tree.
Oh,
and recognize that 12 is really 2 times 2 times 3. So I'm getting ready to kind of break it down to simplify the radical. So Chase, a second ago you said you got lost somewhere, but now you look like maybe you aren't. You're good? Okay. So 2 2's in the radical, don't they get to come out as a single 2? This is what we've been practicing the last couple of days. So these 2 2's come out. So I end up with 2 square root of 3 over 4. Hey, do you guys see how this now reduces again? Wouldn't the 2 and the 4 cancel to be a 1 and a 2? So when you get all the way to the end, this ends up being square root of 3 all over 2. So there's a lot going on there. There's a lot of concepts and skills being combined into one question. I'm going to have you guys try one sort of like that here in a second. But do you have any questions right now?
No.
You ready to try one? All right, number 3, similar to what we just did. Number 3. Yes.
I tried to begin with, and before he went over that example,
Yep.
I had already gone over it, and I tried, it's just 3, and it went into 36, and you can still square root 36 and 6 and 6.
Hang on one
So
second.
wouldn't that still work?
Talking to people, looking over shoulders. Listen up, please. Hey, seems pretty clear. The vast majority of you feel like the answer to this is the square root of 2. So let's see if that really is right. So what you would do here, what I saw you all do is you multiplied the top and the bottom by the square root of 18. This gave you 6 square root of 18 over the square root of 324, I believe it is.
Yep.
And the square root of 324 is 18, just like you would expect it to be based on all that we've done. So if you got to that stage, that's really good. You clearly have rationalized it, but you haven't all the way simplified it. Maybe you saw this. The 6 goes into 18 3 times. So this would give us root 18 over 3. And if you got that far, you clearly know how to rationalize, you clearly know how to simplify, but maybe not all the way, right? This last step is where we consider the 18 as really being the square root of 3 times 2, giving me 3 root 2 over 3, and there you go. I think those of you that had root 2, that makes sense. Okay, so we're going to finish off here. If you want to work on your, we're not leaving until 2:05. If you'd like to work on your WebAssign for a few minutes, you're welcome to do so. We'll get out of here right at 2:05.